going to set myself up here. It's always good to be back. I think my last time was here was almost exactly a year ago. Is that about right? Yeah. And if who was here for my talk a year ago? Oh, wow. Oh, repeat people. Okay, great. I mean, it makes sense. You're a club. My topic a year ago was the Interstellar comet/asteroid Oumuamua. I believe, right? That's what I talked about? Yeah. My head's, I guess, not on straight. But I remember distinctly at the end of that talk, I built that talk up, and everybody had been talking throughout all of the media and the researchers and the telescopes around the world about how this is just the first, right? We found this one because we brought online these big survey telescopes like Pan-STARRS that found that other comet, and you know, there's lots of great ones, and there's the one down by the States that's going to come online very soon, the Large Synoptic Survey, although, however, they got a new name. I think it's been, maybe it's the Vera Rubin Survey Telescope. Anyway, I said, this is just the first, that's what all the researchers are saying, and they found one since then. So I meant to bring a picture, but I forgot. But there's now been a second interstellar object found by research, or that was a researcher out of the Ukraine, actually, a telescope over there. So we now have officially 2 interstellar asteroid/comet things that have been detected flying through our solar system, and it's not a hard bet to say that we're going to find a lot more. But today, so I've been, okay, how do I do this? I go like this? One more. Oh, one more. There we go. So, as some of you know, I'm an astronomer about quasars, right? So that's what I did my PhD in. I spent a lot of time pointing telescopes at quasars. I still do. And that's my expertise. But as we all do, who are interested in other things in the sky, we sort of get down rabbit holes sometimes. And I've been interested in getting down a rabbit hole on Mars, and so I use this as an excuse to start digging. And I think Mars is, I really, really love Mars. It's weird to say, but it's my favorite planet, I guess outside of Earth. So I am certainly by no means an expert on this planet, but I really wanted to learn more about it, and it's particularly because it's where we're going. This is where our robots are going, this is where humans are going to go, this is what our telescopes point out all the time, and I felt like I really didn't have a good appreciation for the planet, and I wanted to. I think the only people who really do are the Mars scientists, the geologists who have turned into planetary scientists and really got a feel for it. So I wanted to dig into it, and I'm going to share what I found with you, with the caveat that I don't really know what I'm talking about. So let's go down the rabbit hole together. So Earth, I subtitled it Earth's Distant Cousin, because as you'll see and as we all know, there's some strikingly similar features, both current and in the past, that really align with what we see ourselves living on right now. And that's just a wonderful picture of Mars to get us started. But to really anchor us, I wanted to, start with the big picture, because the solar system is varied, and it's more than when I wore my solar system shirt. It's more than just this, right? It's more than a line, but that's the only way to really appreciate it in a small little slide. But just to get a sense of where we are, is that we sit 3 planets out, but there's Mars just beyond us and the whole asteroid belt. We all live right nice and close to the sun. And it really starts spreading out after that. The terrestrial planets have a ton of things in common. They may not, at first glance, they're really varied places. Mercury is a big iron ball and intensely hot with no atmosphere of any kind. Really, it's just more of the stuff that sort of gets burned off the surface, that sort of hangs around for a while, a tenuous atmosphere, if you really want to say, and then blows away. It doesn't really rotate. Venus is roughly the same size as us, but it has this crazy atmosphere, and potentially, even in the news just recently, researchers are saying even active volcanoes, like now active, which makes it a really weird place, but also feels very similar with our volcanoes. Mars is the one that I think in most textbooks you would find that they would say Venus is the sister, or the sibling. Venus and Earth are really similar, same size, same gravity. If you just pull away some of that dense atmosphere on Venus, that'd be like Earth, right? but it has this intensely dense atmosphere. I tend to always think of as Mars as more like us for a variety of reasons. So it's about half the size. This is to scale. It's about half the size, yes. So in that sense, it's not like Venus. Venus is like the same size as us, almost exactly. It's about half the size, but if you don't include our water, our oceans, it has about the same amount of surface area. So just land surface area, it's roughly the same. So we would be able to walk the same type of ground. It also, so apart from the size, they have almost exactly the same tilt, which is a really fortuitous thing at the moment. Earth's tilt is very, very stable. And that's because we have this wonderful big satellite here, that's to scale, as many of you know. It's this huge honking thing out there, and it really actually helps stabilize our tilt, and that actually does a lot of things for life. There are some researchers that point to the moon as one of the biggest reasons life has been so stable here over so long, because it is a stabilizing force on our tilt, which of course affects our seasons, and our seasons affect everything, right? So our Earth's tilt, very, very stable. Mars's tilt, not so stable. It can vary wildly from over a large amount of degrees. We just happen to be catching it at this time really close to ours, and in that sense it makes it feel sort of like family. It didn't have to be that way. It does have its own satellites, Deimos and Phobos. I tried to make them as small as possible on this slide without making them disappear, and they're still too big. They're tiny, 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 tiny little things, just tens of kilometers in size. So in comparison to Mars, at almost 7,000 kilometers wide, a little 10-kilometer little object orbiting it, that's nothing. It's, many people for a long time thought they were just captured asteroids. Likely story is more that they're probably ejecta from Mars. So you had huge impacts, smack Mars, shoot stuff into space, and those are just big chunks that hung around for a while. It's almost roughly 2 years longer in its year. These are Earth numbers. Like 1 year on Mars is 687 Earth days. So it takes just a little, almost 2 years to go around. But its day, this is what blows my mind. When I started learning about space and learning about Mars, its tilt is the same, and its day is almost exactly the same. Like the amount of things that need to go into the spin of a planet. You're talking about the condensing of the material. You're talking about things that hit it. You're talking chance encounters, and for it to land so damn close to our day is wild. It's just 37 minutes difference. However, that 37 minutes difference really does mess with the researchers that work on the things that drive around on Mars, because they have to work on a Mars schedule. So for every day, it just slightly shifts, and eventually, if you're a controller for a Mars rover or something like that, you end up working in the night here on Earth just to stay aligned with the day. And they have like UV panels in their offices and stuff to keep them going. It's really interesting. Real commitment. It's like real astronomers. You got to work in the night. That's when the stars are out. So there's a lot of similarities just right there. And the tilt, just as on Earth gives us our seasons, the tilt on Mars does the same thing. Oh, there's I wanted to point these out because I couldn't get them in the slide. They're too small. But look at the size. Little tiny little things. One is slowly falling in towards Mars, and one is slowly going away from Mars. They're really interesting places, but we don't have time. Oh, that was another caveat I wanted to say, is that there's going to be stuff that I don't cover in this. I only have like 40 minutes, and there is so much science on Mars. I'm going to probably miss something that you're thinking about. So because you're all astronomers, I'm sure you want to know where in the sky they are. Where in the solar system they actually are. So this is live. This is a picture from the planetstoday.com. That gives you a sense of where they are. Mars is just down straight from us there. So if you want to, this is also nice to see where the rest of everything else is, like where Mackie and Haumea are. You have Pluto way out on the other side of the sun right now. Neptune's just grazing the sun. And this, I wasn't sure if this would show. I'm sort of piggybacking on your what's going on. But I got a visual from Stellarium here, and so there we got, that's 6 a.m. Today, Mars is there, and Jupiter there, and Saturn is just at top of the S is popping up there in the eastern southeast sky. So if you do want to catch Mars, you got to get up early. But of course, we got to wait for our skies to come back. Okay, back to the beginning. That's just sort of a primer, get us moving. I want to just sort of get through a few basic questions about Mars in this presentation. One is just the basics of the planet itself. We already started with that, with like size and rotation and stuff like that. I'm really, really interested in the case for water. That's what I based most of this presentation on, and we'll really dig into that. And then where do we go from here? What are we doing with Mars soon? So this is. I stole this from NASA's Eyes on the Solar System. If you don't have NASA's Eyes on the Solar System, it's a software package that you can download for free, and it gives you a view of the solar system and everything that NASA is operating at the time. So this is a live quote-unquote view of Mars, like almost to this exact minute. I tried to get it right to this presentation, of where all of the things are all the robotic missions are at this moment. Because there's a lot of them. So Mars Express, so it's in this big orbit shooting down this way. Mars Express is a satellite from the European Space Agency. So it's shooting its way down there. There's the Mars Reconnaissance Orbiter right there. That one's from NASA. There's the Trace Gas Orbiter. So that one's all about measuring the tenuous atmosphere that Mars does have and its interaction with the sun and its interaction with the surface. It's a really interesting satellite. There is Mars Odyssey, another NASA mission, so that's 2 and 2. And then, of course, MAVEN, which is a volatile, all about volatiles, again about the atmosphere, about the materials that are coming out of the atmosphere. So that's 5. Voyager's off in the distance, way off in the distance there. But there is a 6th satellite that's orbiting there that NASA doesn't have it on its Eyes on the Skies, and that is the Mars Orbiter mission from India, which is an incredible satellite as well. So there's 6 satellites there. We are intensely interested in dumping billions of dollars into studying this place up close. And that's just the current fleet. The list of missions that have been to Mars and are now over is much, much longer. Of course, that's just the air, or the space. On the ground, we got a couple of really, really great robots, Curiosity, and I love the selfies that come back from here, especially because, not just because you get to see the panorama behind it and the wonderful landscape, Marsscapes, I should say, but how dusty it is. This gives you a sense of Mars is a really, really dry, dusty place, and that dust hangs in the atmosphere for a long, long period of time. It takes a very long time for the dust to flow down. So just being there, this has been there since 2012, just being there for a year, you'll get caked in a nice layer of dust. And every selfie you get back from Curiosity, the Mars Science Laboratory, it gets thicker and thicker and thicker, and it feels like more rugged, like it's really doing its job. There's a fantastic image from Curiosity, and then the other one that's on the ground right now is, of course, InSight. Now, InSight is not a rover, it's a lander, so it's in one spot. And it's not really great at taking selfies. This is the best one I can get. It's not really built to do that. The Curiosity rover, if I can go back, I can. It has this boom arm that it uses to reach out and drill things and look at stuff. But on the end of it, it has a big camera, so the rover can literally, like a selfie stick, take pictures of itself. Whereas InSight wasn't quite designed with that big, long of an arm. It does have an arm. This is a better picture. This is a computer-generated image of it sitting on Mars. And I love this. This is a much newer mission. This one is, you can do a lot from one spot. So the arm, there's the arm you see right there. But, there we go. But it has these 2 things that sit right on the surface. And they're incredibly interesting instruments. This one is a seismometer. So it literally measures the vibrations in the ground. And it's very, very sensitive. And when they were putting it out onto the surface, because it originally started up on the body here, and then it was put out on the surface by the arm, you can and it's switched on. It can detect when the arm is moving. You can see huge wobbles in its seismometer, but it's now detecting Mars quakes. So you can say for sure that ground is shifting on Mars because of this instrument. And this one has had its share of troubles, but it goes meters into the ground and measures temperature and energy flow and stuff like that. So this instrument was not about surface. This instrument was about under the ground, what's going on below Mars. So with this fleet of, how many is that, 6, 7, 8 satellites and robots at Mars, in space orbiting at varying levels of altitude, and roving around or digging into the surface, we can really bolster our picture of Mars. All right, I said basics, right? So first we're going to start with surface features. The biggest surface feature of Mars is its color, right? Starting basic, simple. Red iron oxide. The surface of Mars has a whole bunch of iron in it, and we know that if you get iron exposed to any kind of oxygen, it's going to oxidize, and it's going to rust, and it's going to turn red. And we have this on Earth, like in Cavendish PEI, or in Santorini, or in a million other places around the world. We have rocks that are just bright red with iron that has rusted in the oxygen that we have. One of the really interesting surface features is less about the hard surface itself, but what it looks like from afar, and that's the dust storms. These happen periodically. This is the most recent one in 2018, and this is the one that took down our friend, the Opportunity rover. I know, R.I.P. Copy. So the beauty of those rovers, Spirit and Opportunity, which landed in, I think, 2003 or 2002, they have had solar panels, and the solar panels kept it going it had as much energy as it could ever need from the sun, so long as they used it appropriately. And as a result of the dust storm, it caked a whole bunch of dust on the surface of the solar voltaic cells, and then it had to shut itself down. So it lasted pretty long, but good job. But these dust storms are really interesting and tell us a lot about the atmosphere of the planet. That took, something like 6 months to really well up and go away. So these are periodic features that show up every few years and basically completely cover the surface, fill up the atmosphere with dust, which then slowly falls back down to the ground. Valles Marineris, we all know, this giant, wonderful canyon that streaks across the surface of Mars. It's huge. I couldn't find an outline of Canada that was white. It was the best color, so I had to use America. Sorry. But it's look at this. This is we think the Grand Canyon is insane, right? If you've ever been to the Grand Canyon, that thing is gigantic. But this stretches across the entire continental U.S., the entire continental North America. It's massively large, and off to its side, so just rotating the planet a little bit, there's Valles Marineris. You have the Tharsis bulge right here, which has pocked with a bunch of volcanoes. Of course, the most famous one is Olympus Mons, which is 3 times higher than Mount Everest. So just these basic features give it such interesting extremes. This massive chasm called Valles Marineris, this huge mountain, this old dead volcano, all these other volcanoes, the dust storms. This is just based on that, and that's like information from the 70s. We already know that it's a dynamic place, right? It's a place that has its own active geology. It seems like a boring, dry desert, but it is a very active place just based on that kind of information. We can get a better zoom in on those. It's really the height of that mountain is insane. So we'll get into atmospheric pressure in a little bit, but the difference in pressure just from the bottom of that mountain to the top of that mountain it's almost like going to space. It has these huge polar ice caps, just like we do, which is super cool. Feels more like home again. This one, I think this is the north. I don't know if I wrote it down. Yeah, this is the north. So there may be some unsureness about how much is water and how much is CO2. I can give you a sense. It's mostly water. So most of the ice you see at the polar ice caps is H2O frozen at that altitude, at that latitude, sorry. So it's H2O mostly through and through. It's minus 140-ish up there, minus 140 degrees Celsius. It's cold. That water's not going anywhere. Depending on the season, you get varying amounts of CO2. So the atmosphere of Mars is mostly made of carbon dioxide, and carbon dioxide turns into dry ice, turns into ice at minus 96, minus 97. So when the north is when the pole is pointed away from the sun, it gets much colder in the north, and the CO2 in the atmosphere deposits on top of this about a meter thick. So huge, huge glaciers of ice with about a meter thick of CO2 sitting on the top. On the south is a little bit different. It is, again, mostly water, but it has a permanent 8-meter thick layer of CO2. So something to do with the way it's tilted, the amount of sunlight that can hit the southern pole, the CO2 doesn't leave in the summer. The CO2 sticks around. It's a permanent layer of CO2 and much thicker. So it's got colder temperatures at the south. Let's take a look at the atmosphere. So, my laser pointer. The atmosphere, right off the bat, 1% of ours. It's thin. Very, very thin. It's so thin that things like water can't stay water. So even if you had a temperature above zero, a little puddle of water is going to immediately evaporate. So liquid water can't live at that pressure. But we'll leave that aside for a second and we'll answer some questions later. So it's a really low pressure. Its breakdown is mostly, as I said, it's mostly carbon dioxide, 96% carbon dioxide. And then it's got, at that point, do you really need to count the rest of it? It's got nitrogen, argon, it's got some other trace gases. Very, very stark difference to our wonderful planet, which has these life-giving chemicals that we need, like nitrogen, like oxygen, like water vapor, and others. So stark differences. And right there, you start knowing that I'm going to be getting to talking about water. There's some interesting questions that are showing up. When you're talking about the atmosphere, and we know that we have these wonderful things on the ground, inevitably you get to these kinds of questions. And there's a really fun sort of ongoing debate in the geological community studying Mars on the oxygen and methane cycles. So at Gale Crater, where Curiosity lives, where it's roving around, it's been monitoring the atmosphere, monitoring the gases that are nearby to it. And this is the amount, basically the amount of a gas, and this is with season, and so spring, summer, autumn, winter, local season. And so you can see that just through into the summer and back into the winter, you have a periodic change, a very predictable periodic change in the oxygen and methane. And methane and oxygen are really, really interesting chemicals. If you go back, we didn't even really bother, it's trace gases. It's like, there's some oxygen in there, whatever. We didn't really worry about it. But Curiosity is seeing some really interesting things. Curiosity is saying, I'm seeing an active atmosphere down here. I can notice that the methane that I measure, the oxygen that I measure is changing. And we all know methane and oxygen as such important molecules for life that raises some really interesting questions. Of course, I don't have some great answers for you. But there's this great graphic from NASA that if you stare at long enough, basically it looks like they're just saying, well, maybe it's this, and maybe it's not. But a quick walk through it. So there is methane. We know that there's methane there, locked probably in the rocks. Due to some way of outgassing, so you can crack the rocks with our Mars quakes that we know exist. The methane that's locked down there can get out. Now, where the methane comes from, you can either have olivine, which is a very common rock on Mars, mixed with water, and you get some methane. So there's no biological thing happening there. It's just chemistry creating your methane. Or you can do microbes. So like right there, you're like, well, you guys don't know you have no idea. But this is a huge open question. It's one of those two. You can make methane. You can make methane with rocks and water. Okay, great. So if this is probably the most likely scenario, because saying the idea that life is there, well, interesting. You need real evidence for that. You can't just say, well, it's probably microbes. So let's call this the most likely scenario. That's creating our methane on Mars. That all right there is an interesting thing, because that implies that there has to be liquid water under that surface to create it. And if there is liquid water there, then maybe we can jump right to a source of nutrients, a source of life for some kind of microbes that's there. Maybe it's both of those things that's doing. Now, that's completely speculative, but the fact that this kind of chemistry is going on is really interesting in general. The implication that there's liquid water under the surface, that sounds really great from an exploration point of view. Then methane outgasses, and you have winds, and you have cosmic things, and stuff gets broken up into other kinds of molecules, and off it goes into the atmosphere. And depending on the amount of light you're getting at the surface, will change the amount of methane that you see or the oxygen that you see, depending on, it's like the way you break down a methane molecule from sunlight depends on the season. And that's what Curiosity is seeing. But the real home run here with a varying view of a varying amount of methane and oxygen in local to a place means that there potentially are aquifers below the surface, and that's really, really interesting. Oh, I forgot about this one. Temperatures. So what is it outside right now? It's like minus a million. I think the wind has it at minus 20 right now. And of course, JPL being in LA, they do everything. Everything's the West Coast, everything's LA, right? So those are the average temperatures for LA. Who cares about LA? At Gale Crater, where Curiosity is roving around, you have temperature ranges of minus 20 to minus 80, depending. The dip isn't actually that large. I mean, this is, what is that? Like in the spring, you have maybe minus 10, and then in the winter, you have minus 30. Like, that's not, like, we can handle that, right? There is times where there has been measurements at Gale Crater where the temperature is above zero, which is super cool, but this is an average thing. So from a temperature point of view, we as humans can handle that, and other life on this planet can handle that, but there is a pressure issue with the atmosphere being so thin. Now let's look inside for a second. We're still going through planetary basics, so I think that was the surface. Yeah, so this is all talking about the surface, and now let's look a little bit below. The underneath the crust of Mars is a huge unknown. It's better now with InSight, the seismograph that's there, but there are some unanswered questions. These are 3 different places. It came with the moon, and I didn't really look at the moon one, so I don't know much about the internal structure of the moon. That's also a really interesting thing to get into, because it was part of Earth, and the rocks there are really interesting. But we know on Earth we have this solid inner core, and we have this fluid outer core, literally a fluid outer core. And then this big mantle section, and the physics of the mantle are really interesting, because the rocks in our mantle are they're not quite solid and they're not quite liquid. They're in this plasticky malleableness phase that allow it to transport heat from the real deep, the right down near the core, transport the heat, bubble it up towards the surface, and transfer it to the crust in the upper mantle. And then as it cools, it falls back down. This is the process of convection, and we all know it well with bubbling pots and stuff like that. The hot stuff goes up, releases its heat, and comes back down. And then you have this circular process called convection within the sun, within the Earth, that creates what happens on the physics of what happens on our surface. And now that's really important from so many different things. It transports heat. It brings nutrients up to the surface. That seems to be something that's really important for life on Earth as well. The idea that not just from a heat point of view, but from a nutrients point of view, pulling stuff up from the ground. Mars we have, so you can see over on the far side there, it has a core. It's denser than the surface because that's what happens as you get closer to the center. Whether it's solid or liquid, not sure. It's probably not liquid because the liquid core on Earth is what gives us our magnetic field. That rotating iron creates that internal dynamo, which creates a magnet. But Mars doesn't have a magnetic field. There's no magnetic field there. There's ancient magnetic they've looked at the rocks and they can see that there was some kind of magnetic field going on, but nowadays that core is probably solid. With its rotation, if it was liquid, it should be a magnet. There is a mantle, but the interesting question again is, what is that phase like? What is that rocks like? What are those rocks like? Because the same process of convection is not happening there. There are no plate tectonics on Mars. There are quakes, rocks are shifting, but the way that our crust sort of floats on this malleable mantle is very different than the way the crust of Mars sits on a solid mantle. And that sort of creates a sort of quote-unquote dead surface, dead volcanoes. And that's why we no longer have an exploding Olympus Mons. So that's sort of planetary basics, okay? Now let's get into the real cool stuff. This is what I really wanted to learn about. I'm sure you've all, anytime you open up your browser or something, we'll see something from the BBC or CBC. Once in a while, you'll see something like this. Because it's a really, really big area of research. And everything that comes out of curiosity, insight, everything that's coming from those orbiters, they're all asking different ways of asking the same question. Is like, what's going on with Mars? Is it habitable? Is there life there? Was it habitable? Was there life there? And one of the biggest and most important things to life, as we know it, is liquid water. And so you have this thing that's called the Mars ocean hypothesis. And that sometime in the past, conditions were correct on the surface of this planet to host a very large ocean in the way that we do. So let's go through some of those pieces of evidence, and then I'll let you draw your own conclusion. This is a great image from NASA that showed what that could look like. All right, this is a wonderful image. It looks like our backyard. If I showed you that picture with no context, you'd probably be like, oh yeah, maybe if I went to Sudbury, or maybe if I went to Arizona, might see it. Yeah, maybe that's where you got it from. Like, it's incredible. That looks like Earth to me. Just the layers. That right off the bat. You look at that, and you can see that there are stacked layers of sediment. The only process that creates stacked layers of sediment on Earth is water. Standing water. Lakes. Well, okay, sorry.
Not true.
Okay, not true. One of the only processes is water sinking down to the bottom and creating layers, stacked layers. Which could create that? More shaking head. Sorry. I've offended someone. My bad. The sedimentary rock that you see on Mars could have been created in standing water. Very interesting. But minerals is one of the really interesting pieces of evidence as well. There are lots of different minerals on Mars, but they all come from basaltic rock. Old lava rock, like these ones, olivine, pyroxene, feldspar. And if you add water to these rocks, if you add water to them, then they turn into other things. They change. And there's a lot of these other things right here you find on Mars. You find those minerals on Mars, which imply that there could have been water there. Surface features. This is an old image. This is from the Viking orbiter. It's old. And you look at that and you can just see, you can feel where the water would flow. How an erosion of liquid would create a river valley, a network of channels just like that on Earth. We see images, we can find tons of images just like that on Earth. And you can look in so many different places on Mars and find images just like this one. They're all over the place. Like these branches going up here. This is a wonderful example of it. that show you in relief the channels that are created by a likely liquid source. That seems like a liquid thing. Whether or not it's water doesn't say whether or not that was a liquid water itself. You can't pull from this image, but the fact that you have channels like that implies there was a liquid of some kind there. Perhaps it was lava that was carving these channels. Perhaps it was water. This is a really interesting one, blown up from this this crater here. This what looks like almost like a river delta that has that was flowing water out into different areas. Really interesting. This is my this is some of the more recent stuff. So this is there's been some work on some images recently discussing what would look like huge, massive erosion events. And they suggest, the researchers suggest, based on what they're looking at, that they think it was tsunami based. So a one-time massive wave that created a ton of erosion all at one time. This is an example. You can see the sort of fluid-like patterns around these craters and these mounds. They suggest that what happened is there was a liquid ocean there. Huge impact from a massive meteorite came and hit the bedrock, because no matter what, just like here on Earth, if a big, huge asteroid, tens of kilometers in size, hit, you would get tsunami-like situation, because you create these, it would hit bedrock and you create these big waves going in all directions. And they even go so far in the same area, so these fluid-like patterns are there, but in the same area, so this looks just like the dirt you have in your house from when you click your boots off. But the scale here is very large. All those little things are boulders the size of a house. So what they're suggesting in this work, based on the spray pattern and based on the calculations they made, is that the tsunami was able to carry these rocks from the impact site in the fluid, in the tsunami, and cast them in this huge direction, implying again some kind of liquid to transport it. And in the final image of this work, they had this wonderful, you would consider it almost like it's not I forget the name for it, the geological name for it, but it goes up and it's sort of a protrusion above the ground. It has a higher elevation than the rest. So there's lots of things like that on Mars and on Earth, and this tsunami has taken out a bunch of it. A one-time erosion event you see up here, and the fluid around it. Really, really interesting stuff. One of the earliest signs of researchers thinking about a global ocean on Mars was based on not this map, but looking at this map, which is sort of showing in relief, showing the topography of the system, giving you, I think I lined that up roughly accurately. You have the Hellas Basin off there, really deep. You have the much higher Tharsis Fault with the old and dead volcanoes. And then the top part, the northern hemisphere of Mars, is starkly contrasted to the southern hemisphere. What you're looking at is a surface that has been recreated, that has been eroded in some way. You can do that just based on counting craters. If you assume asteroids hit a planet from most directions in relatively random pattern, then there should be relatively the same number of craters all over in any given area. But the north is starkly different than the south. And so you need an erosion, you need something to resurface that northern hemisphere. And so what kind of liquids can do that? Lava can do that. Big explosions from Olympus Mons could have done that. Global ocean of water could have done the same. And so they dive into mapping that coastline, mapping this line of that shows the difference between the north and the south. And there are some problems and some questions on whether that is you would expect that the height of that quote-unquote shoreline would be the same all the way along the coast. Just like if you went all the way down one of our continents, everything would be the same. But there are different heights along this coastline, which sort of make it harder to suggest that it was a one-time big ocean that lived there for a long time. There are other ways to get around that, particularly because the Tharsis bulge grew out, was created in the middle of this supposed time for a liquid ocean. But the coastline and the implications of the growth of the Tharsis bulge at the same time makes it really interesting. Because if the bulge was growing, then you're implying a lot of volcanic activity. And if there's enough volcanic activity, you can envision a scenario where enough gas and dust was being launched into the atmosphere that would make it thick enough for an ocean to last for a certain amount of time. You need to have a thicker atmosphere, because the pressure is important, and the thicker atmosphere makes it warmer to keep your water liquid and your liquid from evaporating away. So the combination of the shoreline age and the growth of the Tharsis bulge implies that it would be able to support a liquid ocean of water. So maybe this is true. They're still working it out. The general consensus is that it's probably true, but we need more evidence. The evidence stacks up, but there's always a caveat on a lot of the different questions that you bring up, a lot of different evidence that you see. So they're still working on this, and the interesting thing is the next steps. And I'm just going to talk about the next steps real quick. This one is the Rosalind Franklin rover, which is set to launch this year. This is from the ESA, and this is the great thing, is that most missions that have been sent to Mars don't actually say in their main mission that they're going to search for life. Some of them have, but Curiosity, the Opportunity, and Spirit, the goal was geology, the goal was habitability, the goal was, is there water there? Not always front and center is there life there, is there active life there. And Rosalind Franklin rover is going to do that. But of course, we're all probably anxious for this one, right? This is the Mars 2020 rover, which, by the way, doesn't have a name yet. They're running a naming competition at the moment. I think it's closed, though. There was a voting thing that was going on. So Mars 2020 is a sort of beefed up version of the Curiosity rover. It's based on the same design. It has the same boom arm. It has the same basic idea with amped up instruments on board. Seeking signs of life, ancient life. It's already answered the question, Curiosity has already answered the question, if it was habitable, that in Gale Crater, it would have been a habitable place. There would have been standing water, and it would have been warm enough. But the next question is, can we actually find evidence of the life being there? And that's what it's going to be working on. Even more interesting is that it's going to prep samples. So the next step after this, so doing these two rovers in the next 2 to 6 years, as long as they survive. The next step after that is we really want the rocks back here on Earth. We can only do so much with a rover. So both this rover, Mars 2020, and the Rosalind Franklin are going to be prepping samples, or at least testing out the idea of how you would find and package a sample, and then have it. The next step after that would be to send another rocket to pick it up and bring it back. So it's laying the groundwork for a Mars sample return mission, was sort of like the holy grail of studying rocks, doing it in a lab here on Earth. And the whole, from NASA's point of view at least, there's a step process for Mars that they're working on. So determine whether life ever arose on Mars. That's sort of Mars 2020 mission, the rovers that are going there now. After that is to characterize the climate and characterize the geology. This is sort of ongoing, but with the end goal of sending a human there, and who knows when that's going to happen. But we do know that this is going to happen for sure. So the Artemis program that NASA has begun in succession to the Apollo program is a full space station orbiting the moon in much the way that we have the International Space Station now, but at the moon, so hundreds of thousands of kilometers away. The Canada's already dedicated $2 billion in funding to create the next Canadarm to add on to that. So we'll probably send astronauts to this thing. And NASA's ambitious plan is to have this operational by 2024, which is soon. 4 years. 4 years from now, at least a section of this operating at the moon. The goal is to, the 10 years after that is to go down, back and forth from the surface with humans, and then after that to jump to Mars, with Mars in the distance. And they have these wonderful posters that I just put up. This is the general plan from NASA that the CSA is going to be piggybacking on, as we have done with the ISS and other programs. So the future of Mars is robots, it's sample return, it's humans, it's study up close to answer these big questions like, was there water there for sure? Is there water there now? Can we tap into that water? Can we use that water? And the really even more arcing philosophical question is, how should we treat that place when we get there? Because it should be considered an environmentally protected place, which we haven't really figured out yet. So there's some big questions when it comes to getting to Mars, and we're actually in a place where humans could be going to Mars in the next 15 to 20 years, and so we got to answer them now. Anyway, that's all I learned about Mars so far. Hopefully I'll learn a bit more. If you have any questions, I probably can't answer them, but I can Google them after the presentation. So thanks. There's maybe some easy ones I could answer. Oh yeah.
So when you say how high Olympus 1 is,
yes,
over 69,000 feet, what is the reference point with which that?
There's there's no sea level, but the mountain has a shape of it kind of has it's lifted up, and the base, I don't know, if you look at pictures of it, it's like the ground right next to it. Yeah.
The baseline is the average radius of the planet.
Oh, there you go, Mars expert.
Okay, thank you for the talk.
My
question is about the idea of speculation within a scientific paper.
Yeah, great question.
Here's what we found, here's what we think. How sure are they about their hypothesis when they field it? Because I know it's their reputation on the line. How far can they go with that? What are they really not saying that they truly believe?
Well, I can't answer that question. I'm not a Mars geologist. But my understanding is that the general consensus in that community is that there was likely an ocean there. It's hard to prove for sure, and they would say that. It's hard for me to say. I'm not a researcher in the thing, so it's hard for me to really say, but the general consensus of the community is that liquid water was prevalent in the past, and there was a thicker atmosphere in the past to support it. I think they're all quite happy to stake their reputations on that.
Last month, you'll remember that we talked about sort of an introduction to filters. And I gave you an overview of what they are, what they do, and how they're made. So tonight I'm going to talk to you about how to choose the right filter for your application, whether it's observing the planets or the moon, or if you're trying to get around the issues with light pollution where you live. I also had a lot of interest in the last meeting in special filters, so I am working on part 3 of the presentation, and it should be ready in a month or two. So let's start by looking at solar system observing. And what I mean by that is looking mostly at the moon and the planets. Now, if you recall, in part 1, I presented the idea that filters are used to darken some features in order to make other ones easier to see. That is exactly the case when you use filters to enhance your view of planets and the moon. Now, in most cases, the filters you're going to use to achieve this are color filters. And this is a selection of color filters that are used for solar system imaging and observing that I'll talk a little bit later. So how do you decide what filter of these, and there are many more available to choose from, how do you choose which one you want to use? Well, unfortunately, that is a very subjective question. There's a lot of trial and error involved, and at the end of the day, it all boils down to personal preference. So, as I mentioned, these are some common filters that you would use for planetary observing. And I broke them up by basic color group. And you'll also notice that they're all identified with a number. Now, if you recall last week, I talked about this fellow Frederick Ratton, an English inventor. So these numbers are the Ratton numbers. So these are numbers out of his catalog of filters. So the blue filters, you can see they're all essentially wide band pass filters with their center frequency centered somewhere around 430 to 450 nanometers. Green filters are also band pass filters, but their center wavelength is more around the 520 to 540 range. The yellow to orange filters down here at the bottom, they are all essentially high-pass filters. I don't know if you remember, I talked about different kinds of filters there last month. So they're all essentially the same type of filter. They just have a different cutoff wavelength, starting down around 460 and going all the way up into say 620 or 640. And above that are near-infrared filters, but you can't see those with your naked eye. You can't see infrared with the naked eye. And finally, the plot in the lower right, they're all some more unusual color filters that are still used for planetary work. So any filter that has a magenta or purple color, they are essentially green blocking filters. Oops, wrong button. Sorry. Try to reverse the color. The laser pointer is a little finicky. So you see how there's a dip here, centered around the green wavelengths, around 500 to 550. So anything purple has that characteristic. And filters that are light brown or light orange, they're very similar to a normal orange filter, like over here, but they have additional emission in the blue spectrum, so down here. As I mentioned earlier, there's a lot of trial and error required to decide what the best color filter to use on each target is. Many amateurs have already done this work for us and have reported their findings in various media such as books and websites. But when you combine all of these different sources like I've done here in this table, you'll find that it creates a pretty extensive list. In my opinion, it's making things a little bit too complicated. Having to deal with so many filters, it's kind of like a big science experiment. You have to have your little bucket out there with all the different colors and have to have a lookup table and figure out, okay, what I'm looking at now, I've got to change to this color. So that, to me, that's too much work. So I did my own little experiment, and I looked at many of these different filter types to figure out, what actually do you see when you use these different filters? And for the most part, I was disappointed because the improvement you see is really subtle and very subjective. Now, in all the testing I did, there were some filter types that stood out. The first one is magenta filters. And there's a couple of examples here. The CC20M, that stands for Color Correction 20 Magenta. That's a newer type of color filter that Kodak makes. But they're all sort of in the same family as the Ratton filters. And then the 47 and the 30, those are Ratton numbers. So these filters actually do a pretty good job at increasing contrast on Mars and Jupiter. They help to kind of separate different colors in the planet. So I found them to be quite useful. Another class of filters that were very handy were red filters. Number 23, number 20, 25, and 29 are the most common ones that you'll find. I found them useful on the Moon and Mars. It really helped to improve the contrast on the surface, and it also helped to settle down the atmospheric seeing. Now, the only problem with these filters is, with the naked eye, they are pretty dark. And I'll talk a little bit more about that later. Another pair of filters that I found pretty useful were light tan to light brown colored filters. 81B and 85 are good examples of those. I found that they increase contrast on Jupiter and Saturn. And then finally, for looking at the Moon or Venus, very bright objects, using a variable polarizing filter or a neutral density filter I found to be very helpful. Cutting the light intensity down just a little bit helped the eye to adjust and see more detail. So, this is my short list, a little bit better than the previous table. But if you want something even simpler, and you're looking for a one-size-fits-all kind of filter, there is something out there. There's something called a moon and sky glow filter, which is what I would class as a special filter. It's not really a color filter. And I'll talk a little bit more about that in part 3. It is, by the way, the only filter that I use today whenever I do solar system observing or imaging. So, by this point, I think it should be pretty clear to everyone that when you add a filter, what you're doing is removing the light or blocking the light of something you don't want to see. And what I haven't really talked about, though, is the fact that by blocking some light, you're making the whole image darker. And this can be an issue because for some apertures of scope, you won't be able to use some filters because the view will be too dark. So, in the table here on the right, I have listed pretty much all of the color filters that you're going to encounter doing amateur astronomy. I've even included a number of color correction filters, blues and reds and greens. I've also included in this table my calculation of what the luminous transmissivity of each of those filters are. I don't know if you remember from last month, I talked about luminous transmissivity. It's sort of an average brightness or average blocking of the filter to tell you how dark it is. And I've given you these numbers for two different situations. One is when your eyes are light adapted, or for photopic, in this column here, or if your eyes are dark adapted, so scotopic here. And there is a pretty significant difference. The spectral response of our eyes changes quite a bit, whether they're light or dark adapted. So what this table and graph allow you to do is decide whether or not a filter is going to work for your aperture telescope. So if we take as an example the number 23A red, this is a light red filter. And if we were going to look at something that's fairly bright, like say the moon or Venus, most likely our eyes are going to be light adapted when we're looking at the moon or Venus because they're so bright. So if you take the percent LT value of 27 and you go over here, 27, come up, it's about 100 millimeters or about a 4-inch telescope. So that filter probably is going to work okay as long as your telescope is bigger than 4 inches. Now if you're looking at a darker object, like a planet, one of the planets, Mars, Jupiter, Saturn, quite a bit dimmer, your eyes are not going to be fully adapted to the light. It's going to be somewhere between photopic and scotopic. For sake of argument, let's just assume that your eyes are dark adapted when you're looking at the planets. So the percent LT for that number 23 filter is only 1.8%. So if we go way down here to 1.8%, you're going to need a telescope that's on the order of 8 inches in diameter or larger to be able to use that filter. So that kind of gives you an idea of what you need to keep track of. So that's if you're using these filters visually. Now, if you're planning to do imaging, it's a bit of a different story. Because there really isn't a need to use a color filter if you're going to take an image of a planet or the moon. It's way more effective to use image processing after the fact to pull out contrast or to accentuate colors. It's way more effective than fiddling around with color filters. The main concern that we have while imaging is the atmospheric seeing. Now, filters can be used to help you with the seeing, producing sharper and better focused images. At a minimum, I recommend that you use a UV IR cut filter. This blocks the parts of the spectrum that visually you can't see anyway, and in all likelihood your telescope doesn't do a very good job of focusing. So by getting rid of those parts of the spectrum, it will help to improve the focus and the sharpness of your images. Now, if you want to push that even further, there is another alternative, and that's to use a filter that only allows light in the long wavelength end of the spectrum. So a red filter or a near infrared filter. And these do a really good job at steadying the seeing. The only problem is you get a monochrome image. So if someone like me who does a lot of imaging of the moon, that's fine. But if you're imaging Jupiter or Mars, maybe it's not really going to give you the result that you want. Now, like I mentioned, for visual observing, there is a one-size-fits-all sort of filter as well for imaging. And it is, again, that moon and sky glow filter. It does a really good job of improving the contrast between different colors. So, for example, on Jupiter, we have the belts, the different colors from each other, and the shrinking great red spot, all kind of different colors. Those color differences are enhanced by this filter. And I use specifically the Bader Planetarium version, it's a German company, because they have a UV IR cut filter rolled in all into one filter. So that's my favorite filter for when I'm imaging planets. So now let's change gears and talk about deep sky. The main issue with observing deep sky objects, as we all know, is light pollution. Unfortunately, this problem is getting worse every day. There are a number of different sources of light pollution that we have to deal with. Some are natural, some are man-made. In the figure here on the left, I'm going to try to illustrate for you what the main sources of light pollution are that we have to deal with. The largest source, and perhaps the one that we have the most control over, is local, direct, man-made light. Maybe, can you see that down in the corner there? So this would be light coming from the street lights on your street, or your neighbor's porch light, that sort of thing. Next is the man-made light that we see from the larger surroundings of where we live, scattered off of dust and moisture in the atmosphere over top of you. It's still fairly low altitude, but it tends to cover the whole sky from your perspective. It's what we refer to as a light dome that we see around urban centers. After that, the next source is naturally occurring sky glow, which is coming from way up the top of our atmosphere and is due to UV rays from the sun energizing molecules at the top of our atmosphere, mostly oxygen atoms, energizing them during the day, and then at night that energy is being released as light, and we can see that light. And finally, the last source of naturally occurring light pollution is, of course, the moon. when the moon is in the sky, I think we would all agree it has a pretty big impact on what we can see with our telescope. Now, when we look at our deep sky object, like the galaxy up in the corner there, we're actually looking through all of these layers of light. All these things are adding together with the light from the object before it gets to our eye or to our camera. To give you sort of a better idea of what we're dealing with here, this graph on the right gives us a little bit more information about what the characteristics of each of these different light sources are. So the kind of typical or historical man-made light is a combination of both broadband light, so this is the blue curve here, see there's kind of a broad spectrum emission on top of these individual spikes of emission. So these spikes are coming from high-pressure sodium lights, high-pressure mercury lights, those types of light fixtures. Now, more recently, we've seen an influx of LED-based lights. For example, I think most of the street lights in Ottawa now have been replaced with LED lights, at least in my neighborhood they are. So this magenta curve here is what a typical spectrum of an LED light fixture looks like. And it's two emission bands. A wider ones are centered on green-yellow part of the spectrum, and another one, a very narrow one, way down deep in the blue part of the spectrum. Now, sky glow, it's mostly discrete emission bands coming from different molecules in the atmosphere. The main one being molecules made from oxygen, whether it's oxygen by itself or oxygen-hydrogen radicals, some combination of that. And it's mostly discrete emissions. You can see that the red lines here, that's the sky glow. And as you get into the near infrared, the strength of that emission gets bigger. And finally, the moon is essentially a big mirror, reflecting back at us the same spectrum as the sun is emitting. So it's essentially a big broadband emitter as well. And that's, again, you're way up in the infrared where you start to see some sulfur emission. So this is what we have to contend with. Now, what is it that we're trying to see through all this murk? Well, let's have a look. So these are some emission plots for some common deep sky objects. There are two main types of objects based on the nature of their emission spectrum. Any object that we see because of light being given off by stars is considered to be a broad spectrum emitter. This includes reflection nebulae, globular clusters, open clusters, and galaxies. Objects that we see because of energized gas, like hydrogen or oxygen, they're considered to be narrowband emitters. Examples of this group include H2-rich star-forming regions, or planetary nebulae, or supernova remnants. And I've given some examples of each of those here. So you can see the reference star here, Vega. This is M45. The reflection nebula that's around the Pleiades that you can't really see naked eye. And then this hump here is a typical emission spectra from a galaxy, in this case M51. So they're all broadband. There's light being given off over the whole visible spectrum. In contrast to that, nebulae like the blue lines are for NGC 7000, that's the North American Nebula. It's a hydrogen-rich region. You see very characteristic spikes at hydrogen beta and hydrogen alpha. And then if a brighter nebula, by brighter I mean easier to see with the naked eye, would be a planetary nebula like Dumbbell Nebula, which has a lot more oxygen-3 emission, which we can see with our eyes at night. Well, that sort of gives you an idea of the two main types of deep sky objects. Now, whether or not we're trying to observe a broad spectrum object or a narrow spectrum object has a very big impact on how effective filters can be at improving our views when in light polluted conditions. Now, to make the seriousness of this light pollution problem even more evident, consider this plot here, which presents the brightness of all these different sources that I've been talking about, but plotted on the same intensity scale. So these are physical units of brightness on the left-hand side. And note that I have to use a logarithmic scale to capture the huge variation in brightness that we're talking about. So the shades of gray up here are all the different sky conditions, starting with a dark sky down here. This is a normal sky with man-made light. Then the one above is light pollution by adding local LED streetlights. And then dark sky with the moon is like it jumps way up here. And then light pollution with full moon is way up here. And then, unfortunately, the objects we're trying to see are way down at the bottom, several orders of magnitude lower brightness. Now, as a rough rule of thumb, to be able to detect something, a human, to be able to detect something visually, you need a contrast level of at least 50 to 1. So if we take as an example the galaxy M51, the blue line, under dark skies, it is about 1/10 the brightness of the sky. So it meets this criteria of detection. You could probably see M51 quite well in the dark sky. Now, if you're trying to do that from, say, my backyard in Ottawa, right now, because of the local LED lights, it's more than 10 times brighter sky brightness. So, unfortunately, there's no way that I can see this object from my backyard. There's just too much light in the sky for me to be able to detect it. The only things that can be detected under light polluted conditions are objects that have really high surface brightness. So, for example, M27, you can see these big spikes here. It is just bright enough to get that 50 to 1 ratio that we need to be able to detect it. And all these other things, forget it. You cannot see them under light polluted conditions unless we use a light pollution filter. So, it's got a big problem that we need to deal with. How do I choose the right filter for the job? Well, it's not that easy. Just like with observing the planets, our objective is to increase the contrast of the thing we're trying to see by removing what we don't want to see, which in this case is the light pollution. The additional light being added to the scene coming from the light pollution. Now, the best tool for that is a filter. It is made from using interference technology or reflective type. If you remember last month, I talked about absorptive and reflective types. The reflective type filters are the best for this application. The reason being they can be designed to have very precise cutoff wavelengths and very narrow band passes. So you can tune the filter to show you exactly what you want to see. The best filter of this category to use, it depends on a number of different things. It depends on what kind of object you're trying to see. Is it a galaxy? Is it a cluster? Is it a nebula? It also depends on the type and amount of light pollution you have. It depends on the size and type of telescope you're using. And it depends on the tracking capability of your mount if you're doing imaging. All these things play a role in what filter is best for your setup. Now, to help better understand what the choices are of filters out there, I've divided all of them up into 4 main categories. The first category is called broadband. This transmission plot shows a few examples from this category. You also note I've added a few vertical lines to help us to interpret the data. There are lines for things we want to see. So up here, hydrogen beta, oxygen 3. This is emission from comets, but we won't worry about that for now. Hydrogen alpha, nitrogen 2, and sulfur 2. And there's also lines for things we don't want to see. So these are mercury vapor light emission bands, mercury, we have some sodium light emission bands, and sky glow bands shown in here. So we want to see this stuff, and we don't want to see this stuff. So broadband filter is defined by this large pass band around hydrogen beta, oxygen 3, this big band here. That's what they're characterized by. Now, most of these filters are made for visual use. And so many of them don't have any response to hydrogen alpha. As you can see, the yellow filter there doesn't really have appreciable response to hydrogen alpha. But some of the other ones, they do. It's just kind of some do, some don't. Now, the broadband category can be further subdivided based on the width of this band. And this is a system that I've come up with. I've pulled this all out of my butt. So if you look for this in a book, you're not going to find it. So I've subdivided it up in 4 subcategories. Extra wide, I would say, is any filter where the passband is bigger than 70 nanometers. And that red line there is definitely wider than 70 nanometers. These filters have luminous transmissivity or percent LT values ranging from 62 to 73%. So they pass a fair amount of the light that's coming through. Wide filters are in the 50 to 70 nanometer range and have a percent LT around 45 to 62%, so a little bit darker. Medium broadband filters are 35 to 50 nanometers wide. Percent LTs in the 30 to 45% range. And then finally, narrow broadband filters are in the 20 to 35 nanometer wide range and have percent LTs around 20 to 30%. Now, what is convenient about having this whole range of different subcategories is that there's going to be a filter out there somewhere that is suited for your aperture of scope. Whether you have a big scope or a small scope, you're going to be able to find something that is well suited to your application. So, the second category now is called narrowband. So not narrow broadband, just narrowband. Now these filters focus on a single wavelength of light at a time. The most common being hydrogen beta, oxygen 3, and hydrogen alpha. Now hydrogen alpha is really only of interest if you're doing video astronomy or imaging, because the human eye can't see that wavelength when the eyes are dark adapted. Nitrogen 2 and sulfur 2 similarly are also of interest, but only to astrophotographers, because the emissions of those wavelengths are so faint that you need to use relatively long exposure times to pick them up. Narrowband filters are available in a range of bandwidths. Those meant for visual use have bandwidths in the 10 to 20 nanometer range, and percent LTs about 10 to 20%, so quite a bit dimmer than broadband filters. And those meant for imaging alone have bandwidths less than 10 nanometers wide. The third category is called multiband. These filters are characterized by 4 or more passbands of varying bandwidth. The design philosophy of these filters is not to pass the desired wavelengths, but to block specifically light pollution wavelengths. So when you look at the plot, you can see how the dips in the curve align quite well with where I put undesired wavelengths, the mercury vapor and the sodium vapor. So that's how these filters are designed. Now, because of the broad spectrum response, there's still a lot of light getting through this filter. They provide the best white balance of any LP filter out there, which is why many people who do one-shot color imaging, like with DSLR, for example, really like these filters, because they get a nice, well-balanced color image. Unfortunately, the broad pass bands mean that these filters are rather poor at blocking light pollution overall. Broadband sources, like if the moon is up or if you have LED lights in your neighborhood, they have a big impact on how well these filters work. They greatly reduce their efficiency. Now, if you did want to use these filters visually, they range percent LT values in the 50 to 75% range. So they pass quite a large percentage of the light going through them. So the fourth and final category is new. You heard it first, folks. It's called multi-narrowband. I call it multi-narrowband. Nobody else does. Vendors of this type of filter also call it dual band or tri-band or quad band, depending on how many pass bands the filter has. The idea is to give us the performance that you would get from a narrowband filter, but for multiple wavelengths at the same time. Although they've been around for about 6 years, they really have only started to become popular because of astrophotographers who have been using them to do narrowband imaging with a color camera and getting all 3 or 2, as the case may be, of the desired wavelengths at the same time in one image, instead of taking an image with a separate filter for each wavelength. So that has made them very popular with astrophotographers, mostly people who use DSLRs. Now, these filters can also be used visually, if you want. I've tried it visually, and they do work well. They have percent LT values ranging from 8 to 34%, so kind of in the darker end of the spectrum. In the transmissivity plot I've showed here, I've also included what we could call a poor man's multi-narrowband filter. That's the red curve. Whoops. Back here. So if you look at the red curve here, band here and a band here, but it's quite a bit wider than the other two examples given. So this is actually a medium broadband filter stacked with a UV IR cut filter, giving us sort of a wider version of the multi-narrowband filter. And a couple of us here have used this. Simon has used this combination before, and it is quite effective at reducing light pollution. And in fact, adding a UV IR cut filter to any broadband filter can greatly improve its performance. And talk a bit about that later. So now you have an idea of sort of the spectrum of light pollution filters that are available. This kind of captures all of the different types that you can find out there in the marketplace. But I'm sure that a lot of you probably still don't really have a good idea of how to choose a filter. So I've summarized everything that I've learned over the years into an easy-to-read table. And I'll take you through it cell by cell here. So If your target is an emission-type nebula, so planetary nebula, H2 region, or a supernova remnant, regardless of your light pollution level, it could be dark sky, in the middle of the city, I recommend that you use the narrowest light pollution filter that your telescope or mount tracking will allow. And I'll talk more about that in the next slide. In the case of video or imaging, it would be the mount tracking. As I also mentioned, adding a UV or IR cut filter to an LP filter can further improve the performance of that filter in reducing light pollution. Now, if your target is a broadband object like a galaxy or a cluster, and you are under dark skies, then you should not use a filter at all. If you're using a camera, well, adding a UV IR cut will help, but a little bit, not very much, and probably not worth your time. But if you want to try it, it does help a little bit. Now, if you're looking at a broadband target like a galaxy or cluster, under light-polluted skies, visually, you're out of luck. Unfortunately, there isn't really a filter out there that will help you to visually see more contrast in a galaxy or a reflection nebula. There are some vendors out there who say that their filters do help. There's even one called Galaxy Filter, and the reality is that it's just marketing hype. They don't actually do anything appreciable to improve the view. Now, if you are using a camera, whether it's a video camera or an imaging camera, to look at a galaxy or a reflection nebula, etc., then a filter can help. And your best bet is to use a filter that has pretty good response to infrared and is also sort of in the medium to wide broadband range. IR is important because stars give off a lot of infrared, but there's not a lot of man-made light pollution in the infrared part of the spectrum. Most of it's in the visual band, it makes sense. So using a filter that passes infrared with a camera can really help to improve contrast on a galaxy. Now, one final suggestion I have is for people who are using optics that are achromatic, camera lenses, achromatic scopes, that sort of thing. You may find that some of these optics do not do a good job of focusing infrared light along with the rest of the visible spectrum. And the result is you get really fuzzy halos around stars. Adding a UV IR cut filter can help to eliminate this problem. So, as I mentioned, on the topic of how narrow a filter your telescope aperture will support, shown here is a plot similar to what I showed you a little while ago for planetary observing. It is a different graph, but it's the same basic idea. So, using the percent LT values that I quoted earlier for the different categories of light pollution filter, you can figure out how narrow a filter your telescope setup could handle. So, for example, I believe the narrowband filters were in the 10 to 20 range, 10 to 20% LT. So down here. So that means for those narrowband filters, you need a scope that's in the 6 to 10 inch range. Fairly big scope. Now, this is all based on my own personal experience. People with different vision and different objectives to what they want to see may have a little bit different results, but this is sort of a guideline for you of how to pick an appropriate filter for your size of telescope. Oh yes. If you're using an LP filter with a camera, then you don't need to worry about this graph. You can use them with any aperture scope even down to a 50 millimeter or a smaller aperture camera lens. You just have to compensate by increasing your exposure time. Which is a good segue into the next slide, talking about exposure time. The plot shown here is a series of data that I collected over the years doing all of my various filter experiments. The plot shows how many times longer an exposure time, in just as a multiple, how much longer I could go relative to no filter at all that I could achieve using different filters. So I use acronyms here that you don't recognize, but there's DGM-GCE, that's a extra wide filter. The O3, that's a narrowband filter. These are all narrowband filters up here. There's a hydrogen alpha filter. The AUHC, that's a medium band filter. So you can see as your filter gets narrower, the length of time that you are able to expose for increases. Now, I'm not saying that you have to expose longer. I'm just saying that you are able to. And by being able to expose longer, you are able to collect more data and get a better image, more detail in the image, better contrast, etc. And I'll show you some examples of what I mean a little later. Now that's specifically for nebulae. But if we're talking about galaxies, because they are broadband emitters, adding a filter will always reduce the signal from what you're trying to see. So you have to use more exposure if you're using a filter on a galaxy or reflection nebula or other broadband object. And you can see that in the two curves that I've plotted here. The red curve is my curve fit through the data for a nebula, and the blue curve, which is higher, longer time, was observing a galaxy. So this is sort of my experience, rule of thumb kind of thing of what to expect as you use narrower and narrower filters.